Determine the empirical formula for a compound which is 26.6% potassium, 35.4% chromium, and 38.1% oxygen. The compound has a molecular weight of 294.2 grams per mole. What is the molecular formula? So the first thing I did was convert all my percentages to a mass. I assumed 100 grams of the compound, and that's why I could do that. So 26.6% becomes 26.6 grams, 35.4% becomes grams, and 38.1 grams. Then the next thing I did is I divided by molar mass to determine moles. So whenever I did that, I got 0.6803 moles of potassium. I got 0.6809 moles of chromium, and I got 2.3812 moles of oxygen. And from there, I compared all to smallest molar mass, smaller amount. Alright, so from there I took and I just basically divided this one by 6.6803, which gives me 1. Chromium, the numbers were almost identical, so I put it as a whole number of 1. And then when I divide oxygen's moles by 0.6803, we get a 3.5. Notes here, we cannot have a half of an element. We can't have half an element, so what I do is I multiplied everything by 2, which made my ratio become 2 potassiums to 2 chromiums to 7 oxygens. So it becomes 2 to 2 to 7. 2 times 1 is 2, 2 times 1 is 2, 2 times 3.5 gives us 7. So our formula, our empirical formula, our EF, becomes K becomes K2 CR2O7. Now, the second part of the problem said the compound has a molecular weight of 294.2 grams per mole. And to determine molecular formula, we compare, to get the molecular formula, or the molecular to get the multiplier, it is where is it? To get our multiplier for our thing is going to be molecular formula mass over empirical formula mass, and that's going to give us a multiplier. When we determine the empirical formula mass, we find out that it is the exact same number, so that means our multiplier is 1, so therefore our empirical formula and molecular formula are equal. So our molecular formula is K2CR2O7 as well, and again, the whole point is we could have cheated and saw that this is an ionic compound and just skip some of the work. You can do the work to verify, but you'll find out that one happens the same. But when it's covalent, all nonmetals, you're going to have to go through because sometimes it's not. All right, yes, sir. So whenever I determined my moles for each one, that was the smallest one. So we're looking for a ratio of elements to each other in the compound. So I'm going to divide each one by the smallest molar amount. And that's going to give me this. So we're looking for a close to whole number ratio. So this one comes up to be 1. This one comes up to be like 1.001, something like that. And then this one gives me a number of 3.5. Anytime you have a number that's a 0.5, we have to multiply everything by 2. Numbers like 0.2 and so if it was like 0.2 or 0.8, we just round. It's going to become a 4 or go down to 3. But that 0.5, that's when you have to multiply. And you usually don't get numbers that are like, you'll get a 0.5, but you usually don't get other decimals that would even make you think you had to double it. This is the only one that happens. It's just the way it happens, the way the ratios happen. All right. So kind of moving forward, next concept, and this again is a concept that you probably remember or will remember how to do once you see it again. We are doing reaction stoichiometry. All right. So basically, we're going to compare one side of the reaction to the other, or one compound in the reaction to something else. So first step in reaction stoichiometry is always balance the equation. First step, or ensure that the equation is balanced. B-A-L-A-N, balance equation. So let's look at this equation here. Take a moment, try to balance this equation, make sure everything matches up, and I'll come back and we'll verify. Looking at this, you've had a moment to kind of look. First thing that you should notice, what's the main thing that's out of balance that you should notice first? All right. So the carbons are out. I'm looking at oxygen. Oxygen, we have 1, 2, 3 here, and we have 2, 1. That's 3. So oxygen right now is balanced, but the C's are out of balance. So how can I get the same amount of carbon on each side? All right, I'll put a coefficient of 2 right there. When I do that, that changes my oxygen as well. Now I have 4 oxygens plus 1 is 5. So I'm going to have to make some changes over here as well. But the other thing, let's look at, we have 6 hydrogens. We only have 2 hydrogens here. So how can I get the hydrogens the same? Put a coefficient of 3. So that's going to give me 6 hydrogens. Now I have 6 hydrogens on each side. All right, so with doing that, that gives me 2 times 2 is 4, 3 times 1 is 3, so 7 oxygens total. I have 3 oxygens over here, so if I put a 3 there, that gives me 6 plus 1 oxygen, and it's balanced. Now, just kind of picking your brains to see if you remember what specific type of reaction is this? Remember, we have synthesis, decomposition, double displacement, single displacement, and combustion. All right, so recall that synthesis is where you have 2 smaller things coming together to make one large thing. Decomposition is going to be a large compound breaking up into smaller compounds. Double displacement is 2 compounds where the metals replace each other. Single displacement is where you have an element and one compound, and the element displaces another element in the compound. And combustion always involves a compound that's being combined with oxygen. So this particular one is combustion. And if it's an organic compound, the products will always be CO2 and H2O. Think about cellular respiration and photosynthesis. Those are, well, one's a combustion, one's a reverse combustion, but those are the same. All right, so the second part of this question said draw a particulate diagram. I'm never really going to ask you to do this, but I am sometimes going to draw a particulate diagram and want you to recognize what's going on here. So just to kind of show you what's happening here, so since this is combustion, we're going to kind of draw what's happening here. So I'm going to represent carbon by a red circle, and y'all don't necessarily have this ability in your notebooks, but I'm going to represent hydrogen by a green circle. So our compound is C2 H5. Oh, I need an O2, don't I? Let's find a color for O. Let's do yellow for O. All right, so C2H5OH. And my hydrogens are green. So one carbon is going to have 1, 2, 3. The other carbon is going to have 1, 2. And then the last carbon, the last bond on the carbon is going to have an oxygen and another hydrogen attached. So there's our basic compound. It's going to react, and it forms CO2. And so we have 2 of these. And so it's going to form CO2. So we have my O2 as well. I'm going to have to draw that. C O plus H2O. And I forgot to draw my my plus O2 over here. So I'm going to do this plus. Alright, so we had 3 of these. We only had 1 of these. Sorry. We had 2 of these. And we have 3 of those compounds in the end. Alright, so that's just kind of what a particulate diagram is going to look like. Sometimes the particulate diagram will actually draw all the structures out. So it would have drawn 3 structures of this, 1 structure of this, 2 of these, and 3 water molecules. But that just kind of gives you the idea. Now, getting into the stoichiometry part of it, and seeing what's happening here, just taking it as step by step to refresh our memory. It says determine the amount of iodine produced when 145 grams of potassium iodide reacts with excess copper 2 chloride. Alright, so a couple of things to remember when we're looking at this equation. Whenever I say excess copper 2 chloride, what does that excess tell us? What does that mean? Huh? It's going to end up being left over, meaning there's so much of it there, the amount really doesn't matter. We're never going to use it all up. So we have plenty of extra there. So what we're needing to look at is we want to know how much iodine is produced. So this is the one we want to know. This is the one that we know. We have 145 grams of it. What is the 145 grams really useful to us, or what do we really need to know it in to be able to compare? We need to get to moles. So we need to know moles of that. All right. The way the question is written, we can just kind of go start it out. So we'll go. The other thing to pay attention, I said always check and verify that it's balanced. Anytime you see coefficients in the equation, you can assume that it's balanced. So we'll start off 145 grams of potassium iodide. What's my next step? All right, I need to convert the mass to moles. So I have 1 mole. How much does 1 mole of potassium iodide weigh? Say again? 165? All right. What would be my next step in this equation? This is the part that you may need to remember is mole ratio. Does anybody remember where the mole ratio comes from? In the equation, we look at the coefficients. So if we're trying to get rid of potassium iodide, we have 4 moles of Ki, and we're going to compare that to how many moles of I2? 1. And all that does is gives us a conversion to that. Now, yeah, just the coefficient. So all I'm looking at is the numbers right there. When there's not a number, we always assume 1. All right, and then the last step would be to go from moles, 1 mole of I2, and then we need the molar mass of iodine, which is 126.9, so 127 times 2. It's 254. All right, and so we would solve that out, and that gives it to us. So step 1, convert given to moles. Step 2, I guess cross mole ratio. Step 3, if required, convert unknown back to grams. So when I teach this concept in Chem 1, one of the things I'm real bad about is writing the formulas, every single one of these formulas, how to do this on the board and just leaving them up there. A better way to think about this is think of it in steps. What do I have to do first? If I have grams, I need to get rid of grams. I want to be in moles. And then when I'm in moles of, so right here I'm in moles of potassium iodide, where's the next thing that I want to go to? The next thing I want to go to is I want to go from potassium iodide, so I want to get rid of that potassium iodide, and I want to go to iodine. And then from there, I want to go back from moles of iodine to grams of iodine. Yes? Balanced. Um, but like I said, on this one of the things to notice, since coefficients are already in the equation, anytime you see coefficients present, you can just about 99% guarantee it's balanced. Um, or, and sometimes they balance a specific way because they want it to come out like that, especially with an excess reactant and all of that. So, but that's kind of what's going on there. So let's look at the next one, and I think I'm going to get y'all to work this one. Yeah, I want you to go ahead, take a minute, try to work this one on your own. So, check for balance. And then solve the problem. And I'll go ahead and read it off and then let you take a moment. So baking soda, which has a chemical formula of NaHCO3, or sodium bicarbonate, is often used as an antacid. It neutralizes an excess hydrochloric acid secreted by the stomach. So we have the chemical reaction NaHCO3, which is in solid form, plus HCl, which is aqueous, meaning it's dissolved in water, will react to form sodium chloride, water, and CO2 gas. So looking at these just real quick, we're going to verify. So we're going to verify a couple of things in this on this reaction. One sodium reacts, and it has one sodium. We have two hydrogens here. We have two hydrogens here. We have one carbon here, one carbon here. We have three oxygens, and we have 1, 2, 3 oxygens. So that one's balanced. The next part of the statement says milk of magnesia, which is an aqueous suspension of magnesium hydroxide, is also used as an antacid. MgOH2, which in solid form reacts with two hydrogen chloride molecules to form two water molecules and magnesium chloride in the solution. And then the question is, which of these is a more effective antacid per gram? So we're going to do a reaction. Reaction A is going to be with this. Reaction B is going to be with this. So just kind of getting you started, that means you're going to have to kind of solve it twice. And what is going to be our given amount that we're starting with for each one? Really doesn't matter. It says per gram on there, so you could do it just 1 gram of it. So I would start off, I would say like 1 gram in a NaCH03, and then so what I'm gonna compare each one to is how many grams of hydrogen chloride does it get rid of? Yeah. All right. So that, yes. Because, so this is reaction A. This is reaction, No. So what's going on is we want to see how much hydrochloric acid we can neutralize with baking soda and how much can we neutralize with magnesium hydroxide. So there's two different equations going on here. And each one we're looking at 1 gram, and just for sig figs reason we can say this is 1.00. I'm going to set up the first equation and then let you do the second one on your own. Alright, so we want to go to moles of NaHCO3. Does anybody have the formula mass for sodium bicarbonate baking soda? Plus 1 baking soda, and I got 0.0343 moles of HCl neutralized with magnesium hydroxide. So looking at these, which one was more effective at neutralizing magnesium neutralizing hydrochloric acid? Magnesium hydroxide, milk of magnesia. All right. So what this basically tells me, and or what it tells a consumer, that most people aren't going to, whenever they're deciding which antacid to buy or anything like that, it's not going to do this math. But what this tells us is we need a smaller dose of milk of magnesia to take care of acid reflux than we do of baking soda or something like Tums that's not magnesium based. So this kind of helps, like on the pharmaceutical side, it helps determine what dose we need to get the proper neutralization or whatever that we want to take care of. Or it tells us that if I'm being cheap, I guess, and I just take my box of baking soda, open it up, and take spoonfuls of baking soda, which is very, very nasty, and trying to neutralize an acid reflux thing is going to take me 2 or 3 spoonfuls of baking soda versus one little cup, medicine cup of milk of magnesia. So that's just kind of which one do you want to choose type thing. All right. Now, so again, where I'm wanting you to see is the step change from Chem 1 to Chem 2. In Chem 1, you only looked at one reaction at a time, and we looked at it within that one reaction. So from here, they're giving us 2 reactions, and let's kind of talk about what's going on here. So in an industrial method for the production of the element, that's a lot to say. From the production of the element zinc from its ore to roast the crude ore in oxygen is to roast the crude ore in oxygen and then react it with carbon monoxide. The following reaction describes the chemical process. So we have zinc ore, which is zinc sulfide. So it takes two formula units of zinc sulfide reacting with 3 moles of oxygen to form 2 zinc oxides and then 2 moles of sulfur oxide as well. So one of the things that we're going to pay attention to, because this is kind of our key component that we're going to need, and then we look down here at the next reaction. We have zinc oxide reacts with carbon monoxide to form zinc and carbon dioxide. So this whole process is a 2-step process, and then it gives us this question. A 10 kilogram sample of an ore containing zinc sulfide was chemically treated according to the reactions described above, producing 2.85 kilograms of zinc. Determine the percentage of zinc sulfide contained in the original sample of the ore. So let's kind of break down some things that are going on. So the first thing I want to look at is I want to do my stoichiometry to find out what's happening. So right now I have this. I have 2.85 kilograms, and I need to know zinc oxide. Why am I choosing zinc oxide there? Say zinc oxide in both. So if I can get here, I can determine here as well. So I'm going to start off with 2.85 kilograms. Now, is this unit useful for me in converting in moles? No. So what's the first thing I need to do? Convert it to grams. So how many grams is 2.85 kilograms? Remember that there are 1,000 grams in every kilogram, so it's going to be 2,850 grams of zinc. All right, so what's my next step here? What do I need to do? I need to get to moles. So I'm going to go, for every 1 mole of zinc, there are 65.38 grams of zinc. That gets rid of my grams and it gives me moles. All right, next step. I am going from zinc to what compound? Zinc oxide. All right, so looking at our mole ratios here, I didn't verify if this one was balanced, but 1 zinc, 1 carbon, 1 carbon, 2 oxygens, 2 oxygens, so it's balanced. So it's 1 to 1. That's always nice. Technically, that cancels out in the reaction. You don't really have to do the multiplication there, but I like to show it just to make sure. All right, and now we are getting to this next point. Now that we're in zinc oxide, we can go from zinc oxide to this one, right? To zinc sulfide. So for every 2 moles of zinc oxide, how many moles of zinc sulfide are there? And again, since it's 2 to 2 ratio, it really cancels itself out, but I want you to see why this factor works. And then we need to go back, we need to get back to grams because we're going to compare this answer to this 10 kilogram sample and see what our efficiency was. So for every 1 mole of zinc sulfide, if you do the formula mass, I'll go ahead and give you that number is 97.44. So somebody tell me, what do we get as far as grams of zinc sulfide? Yeah, because we're dealing with 2,850 grams initially, so okay. So, all right. So let me just. All right. So what was it again? 4,247. All right. So what you're going to do there is you're going to compare this number to this number. We're basically just trying to find the percent composition of zinc sulfide in the original ore. Um, and so that gives us a percentage of like 42.5, something like that. Check my math on that. So in this process, if we have 10,000 grams of a sample ore that has zinc sulfide in it, and we are only able to produce 2,850 grams of zinc out of that ore, then that means that the original ore was 42% of that sample. Yes. Um, I just went, all right, so they had 10 kilogram sample right here. And I just converted kilograms to grams. There's, again, 1,000 grams for every 1 kilogram. And at this point, I'm kind of taking it for granted that metric to metric conversions, y'all have a good hold of that. Um, so